It is very unusual for new programming languages to spring forth fully formed, without being based on earlier languages. Therefore, it is useful to take a look at earlier programming languages, so one can see how programming languages evolve, sometimes from earlier versions of the same language, and sometimes from other languages. The chart shows how the evolution of various programming languages took place. You can see how Fortran 1 led to Fortran 2, and in turn to Fortran 4, Fortran 77, and Fortran 90, which is similar to predecessors in some ways, and very different in others. You can see how Algol's various versions led to the development of Pascal, and in turn to Modula 2 and Modula 3, as well as Oberon and Ada. You can see how Algol also led to Simula and Smalltalk, and how various dialects of BASIC led to Visual Basic. You can see how CPL led to BCPL, and in turn to B, to C, to C++, and to Java. And you can see how Lisp led to Scheme and Common Lisp. This kind of evolution has also happened to human languages, and explains why Spanish, Portuguese, and Italian are very similar, and how Russian, Bulgarian, and Serbo-Croatian are a lot alike. Except in those cases, it took centuries for this to happen. With programming languages, it has happened in only 50 years. A programming language is simply a way that we express how computation is to be carried out. Since programming languages are necessary to help express the ideas behind algorithms, it should be no surprise that their history parallels that of computers, and that their history is frequently independent of computer development. Few people today know who Konrad Zuse was, or what exactly Plankalkül was. But Zuse came up with a way to express numerical algorithms more than a decade before Backus and his group developed Fortran. And Alonzo Church's lambda calculus became the theoretical underpinning for much of the theory of computation and the development of programming languages. We have to understand that the need to describe calculations is ancient. This page shows an algorithm that is a description of how to calculate the width that appeared in cuneiform writing as adapted by Donald Knuth. We have the volume and the cross-section, but we can work backwards to find the width. But why does this work? Here you see the algebra that leads to this calculation. The volume and cross-section for this rectangular cistern is length times width times height plus length times width. If the length and height are the same, it becomes length squared plus length times width. We can factor out length times width to get length times width times the sum of length plus 1. We can substitute length equals 5, and this simplifies to 5 times width times 6 equals 120. Dividing 120 by 30 gives us the width, which is 4. The calculation is a little quaint, but it shows how even the ancients were thinking about how to do more involved calculations. Charles Babbage received a grant of £1,700 from the British Parliament to develop the difference engine, a machine that would automate many types of calculations. In the middle of the project, Babbage abandoned it to develop the more complex analytical engine, which would have been the first programmable computer had he been able to finish it. But having changed the project without finishing the difference engine, Parliament refused to grant him any additional capital, and developing and making the tools that he needed for the work were very expensive. Contrary to popular opinion, the technology to complete the analytical engine existed in Babbage's lifetime. It was a mechanical device and not electric. And the portions of the engine that were completed worked exactly as Babbage had designed them. Although the machine was never completed, this did not stop the Babbage protege, Ada, Countess of Lovelace, from writing programs for the analytical engine. For this reason, Lady Lovelace, who is Lord Byron's daughter, is considered to be the first computer programmer. Konrad Zuse was a German engineer who built the first electronic digital computer. This was done in Nazi Germany, and Zuse had to do so in his spare time, because the Nazis, in their limited intelligence, didn't recognize the potential value of the work. Although none of his computers survived the Allied bombing of Nazi Germany, his notes about the planned language of Plankalkül did survive the war, but they were not published until 1972. The language was never actually implemented. There are no Plankalkül compilers in existence, but the language included data structures such as arrays and records, and allowed for the use of invariants, mathematical expressions that will be true during the execution of certain spots in the program, a very useful concept in software design. This slide shows an assignment statement that sets the value of a sub 5 as a sum of a sub 4 and 1. This first line indicates that we are adding 1 to a value in the array A and storing it in the array. The second line shows that the subscripts for the two operands are 4 and 5 respectively, and that they are both n-bit integers. The language looks almost hopelessly clumsy by the standards of today, but it is important to remember that this was designed 12 years before Fortran and 24 years before C. Originally, all programming was done in the native language of the computer. In other words, using the binary codes that comprised their instructions. This was difficult to do because it was difficult to envision any larger portion of the program than the instruction that you were currently writing. One of the first things that programmers did to make it easier was to represent the binary numbers in base 8. Base 8, or octal numbers, can be converted to and from binary or base 2 numbers more quickly than converting binary to or from base 10, or the decimal numbers that we use. Later, programmers developed symbolic names for the operation codes, or opcodes, and the operands of the instructions. This made it easier to write the programs. After they checked to make sure that the program would work correctly, they would simply hand translate it to machine language, and then it could be entered into the computer. Eventually, programmers discovered that the task was so mechanical that it could be automated fairly easily. That meant that they could write programs that would do the translation for them. Since these programs assembled the translations, they were called assemblers, and the languages became known as assembly languages. As we discussed earlier, many of the earliest computers were used for large-scale numerical applications. So for this reason, it makes perfect sense that there were so many attempts to create a high-level programming language for numerical applications. Speedcode, A0, and speed coding were all attempts to do exactly this. But they were slow to translate and slow to execute. And it took a while before there were computers that had the necessary hardware to support floating point arithmetic. Before, that all had to be done by software emulation. For these reasons, it took a while for such efforts to become successful. Backus and his group at IBM worked on Fortran from 1955 to 1957. The language was based partially on the IBM 704 computer, which remained for a long time the standard for what Fortran did. It included real numbers and integers, as well as several control statements, conditional and unconditional gotos, and counting loops using the do statement. It also included formatted and unformatted input and output that included the use of files. Fortran was popular enough that there have been several versions since then. Fortran 2 added subroutine and function calls, and common blocks of data that could be shared by the program and subprograms. Fortran 3 introduced a few machine-specific features and was never publicly released. Fortran 4 removed a few hardware-specific features and added Boolean variables and expressions, explicit variable declarations, and replaced the arithmetic if statement with the conditional if statement. Newer versions in both 1977 and 1990 added additional features, including more structured control statements and a character-based data type. Fortran is a line-oriented language. Generally, the rule is one statement per line and one line per statement. This goes back to its origins, when Fortran programs were recorded on punch cards and then read in using a card reader, and position on the line is also important. Statements are generally written in columns 7 through 72. If the letter C appears in column 1, then that line is a comment and is not translated by the compiler. Statement numbers appear in columns 1 through 5. The only statements that need statement numbers are those being explicitly referenced, such as using the statement as a destination for a goto, as the end of a do loop, or as a format statement. The number of the last statement included in the do loop on this slide is 102. If you needed to continue a statement on the next line, you simply placed a character in column 6. It could be any character, although most programmers develop their own styles for this. Fortran 1 and 2 did not have explicit type declarations. Variables beginning with I, J, K, L, M, and N were integers. Variables beginning with other letters were real numbers. If you wanted to work with an array, you declared it as such using a dimension statement. If you wanted to have variables beginning with a particular letter have a different data type than you would have implicitly, you can use an implicit statement to change it, as you see here. In this program, variables beginning with A, C, R, and S are also integers, although normally they would be real. Variable assignments work in the same way as they do in other languages. Input is performed using a read statement. The first of two numbers in parentheses indicate the device code for the input statement. By convention, 5 is usually the card reader, 6 the printer, and 7 the card punch. Other numbers can be used for files after they are open and the device codes assigned. The second parenthetic number is the statement number for the format statement being used. I3 means the next 3 columns on the card, or in this case, the first 3, are an integer value. Fortran 1 and 2 only had the arithmetic if. In this case, if listlen is negative, the program jumps to statement 106 because the first statement number after the parentheses is 106. If listlen is 0, it jumps to statement 106 because the second number after the parentheses is 106. And if it's positive, it jumps to statement 101 because this is the third statement number after the parentheses. In the second if statement, it goes to 101 if listlen minus 100 is negative, because this indicates that the value is within the allowable range. The continue statement is the no-op or no operation. It allows the programmer to attach a statement number to a card that can easily be rearranged in the deck if necessary when debugging a program. The do statement is for counting loops. Counter is initially 1, and its highest legal value is listlen. Since there is no third value listed, the increment value is the default value of 1. The only new feature in this portion of the program is the write statement and its format statement. The format statement contains 2 fields. The first, beginning with 33H, is called a hollerith field, meaning that the 33 characters starting immediately after the H is a quote. This is used because early key punches didn't have quotation marks. The first character in an input was used for printer control. Beginning this line with a blank, move the printer to the beginning of the next line. The return statement indicates the logical end of the main program, and the end statement marks the physical end of the main program. This program written in Fortran 4 illustrates some of the changes in the language that appeared when Fortran 4 came out in 1962. These were followed by the first industry standardization of Fortran in 1966. There were now explicit variable declarations and additional data types. You now had integer, real, double precision, complex, and logical. And you could use these statements for declaring arrays as well as scalar variables. There was now unformatted input and output that didn't involve files. The asterisks that you see here indicate that the device is the standard input device, whatever that may be, and there is no format statement for output. the logical if statement now appears to avoid overloading the equal sign, that is, giving it too many different meanings, and to avoid using the less than and greater than signs, which were not always on keyboards. They use two-letter abbreviations with periods on either side as a relational operator. And or, true and false, could be used also with periods on either side. You could use the if statement to jump conditionally to another statement, or to perform some operation conditionally. Since there was no structure for if then else, this was implemented by using conditional and unconditional gotos, just as we still do in assembly language. Here you see the use of unformatted output. In this case, we still use a device code of 6 for the printer, because we want to state the device explicitly, even though we are not using a format statement. Fortran 77 saw additional changes. The most significant changes involved the use of block structure for if-then and if-then-else. Some compilers included a while statement that did not actually become part of the standard until Fortran 90. Another change was that you didn't need the parentheses for input and output to standard input and output devices. You could write the format statement number and a comma, or just an asterisk and a comma for input. You also see the start of the if-then-else construct. The word then appears at the end of an if statement. Every statement until the else or end if statement is performed only if the condition is true. Output to a standard output device was a little different. The word print was used instead of write. After this, you simply write the statement number or an asterisk and then a comma. You can also see the end of the if-then-else here. In this case, there's only one statement performed if the condition is false, and then the end if is followed by the end statement, marking the physical as well as logical end of the program. Fortran 95 saw additional changes that include the use of inline comments, beginning with an exclamation point. Implicit none does not allow for implicit typing, which came to be considered poor style. You can see here the introduction of the end do, which is more readable than ending do loops with a statement number that had appeared in the do statement. Here you can see the end of the program. Overall, it's clear that Fortran has evolved significantly from 1957 to 1995, and it continues to evolve. IBM came to dominate about 90% of the mainframe computer market. The concern was severe enough that the United States Department of Justice filed an antitrust lawsuit against IBM in 1969. The success of Fortran made a lot of computer professionals afraid that IBM would dominate the computer industry, which of course it did. GAM, the German Society of Applied Mathematics and Mechanics, worked together with ACM, the Association for Computing Machinery, to develop an alternative to Fortran. They both organized committees that were to design universal languages. These efforts led to ALGOL, the algorithmic-oriented language. While the language never became popular in the United States, its derivatives included PL1, Pascal, C, and Ada. There were 4 specific goals for ALGOL. Firstly, it should be close to standard mathematics. Fortran had strayed a little from this, especially if you looked at how logical expressions were written. ALGOL should be useful in describing algorithms, something that was really not true about Fortran. ALGOL programs had to be compilable. This was essential because if they couldn't be translated into something that ran on a computer, the language would be useless. But this was a challenge in 1958, when most of what we know about automated translations of anything was still unknown. ALGOL should not have been tied to a single computer architecture. Fortran was heavily tied to the IBM 704, which had a strong influence on the design of several statements in Fortran. By decoupling the language from the hardware, it gave both the language designer and the computer architect more freedom in future design work. ALGOL saw some use in Europe and very limited use in the US, but it was important because of its influences on other languages. The most significant influence was in the use of a notation known as Backus-Naur form, or BNF, which is used to specify syntax in programming languages. Also, Burroughs' use of prefix notation, developed by Jan Lukasiewicz, helped lead to the use of stack-based architectures. This is now a standard part of any language's design. This is a sample of a program in ALGOL. We indicate here the size of the array A, as well as the result being passed back, which is Y, and the indices at which this value appears in the original matrix. ALGOL uses the colon and equal signs as an assignment operator, so the equal sign by itself can be used as a test of equality. By now they knew that using the same symbol for more than one purpose complicated the translation of the program. Also, statements end with a semicolon, allowing programs to be in a freer format with statements spread out over more than one line, and more than one statement on a line if desired, although it was generally considered a bad idea by this time. The for loop appears here and is somewhat more readable than the do loop of Fortran. Very little thought was given as to how this would be executed on a computer. The ALGOL standard did not include input and output statements, which meant that each implementation handled it differently, and therefore programs written for different ALGOL compilers were incompatible with each other. Nevertheless, many ideas that came out of ALGOL found their way into other languages, many of which are still popular today. The first application to run on the first commercially built computer was projecting the results of the 1952 presidential election for CBS News, and the computer was originally built for the Bureau of the Census. So the need for a language for business applications should surprise no one. The U.S. Defense Department sponsored the effort, which led to COBOL, the Common Business-Oriented Language. It was standardized in 1960 and re-standardized several times. Part of the reason for its success was the obvious need for such a language, as well as the big push it got from Grace Murray Hopper, whose phlegmatic language inspired much of it. COBOL succeeded for several reasons. The language is self-documenting. Well-written programs in COBOL do not necessarily need a lot of commenting, although it is available in COBOL, because programs written in it almost read like standard English. COBOL introduced the record structure, which made it very easy to organize data, something very important to the business community. The ability to format data was considered very important as well. If you have any doubt about that, take another look at any pre-printed statement that you've received. The picture clauses used in COBOL made it easy to maintain complete control over how numbers were displayed and printed. The syntax of COBOL has been a major influence on most database languages, including SQL. COBOL is also line-oriented and uses two margins. The A margin begins from columns 8 to 11, within which the names of various divisions, sections, and paragraphs must begin. And the B margin begins on or after column 12, where COBOL statements can appear. COBOL programs consist of 4 divisions: the identification division, the environment division, the data division, and the procedure division. The identification division allows the programmer to provide basic identification about the program, its use, its author, and so on. The only required item is the program ID, which contains the name of the program. One might choose to include the author's name, date written, date compiled, which is actually added to the program listing by the compiler. The environment division allows the user to add pertinent information about the environment: the computer on which it is being compiled, the computer on which it will run. This is in the configuration section. The input-output section allows the user to specify the files and devices being used, and to specify file organization, access mode, and other information. The data division is where the data used by the program is defined. Every data item must be specified, and the programmer can state the exact layout of each data item. The file that you see in this slide has standard labels, which pertain to files stored on tape. Files in COBOL are viewed as a collection of records, and usually requires that we know how many characters there are per record. Numeric entries are indicated in the picture clause by a 9. 9 with 5 in parentheses indicates 5 digits. I didn't have to write it this way. I could have written 5 nines if I chose, but this is shorter. The V that you see indicates where the decimal point goes if it is left out of the input. The X's indicate character data. Where you see the word filler is a field that will be ignored if they are in the input, or that where spaces will be skipped if they are in the output. The Z's indicate lead zeros. If the number is not large enough to require these extra spaces, they are replaced by lead zeros. There are other characters with which they can be replaced, including blank spaces, but they don't appear in this particular example. In addition to the data being read and written, there is also a place where you can specify the data that you use in the program, but never use for input or output. This is called working storage and does not require the usual information about the file. The procedure division is the remainder of the program, with the program's executable statements appearing here. COBOL programs are organized into paragraphs, and the standard convention is to have a number at the beginning of paragraph names. The main paragraphs typically have names beginning with numbers evenly divisible by 1,000, subsidiary paragraphs divisible by 100, and their subsidiary paragraphs divisible by 10. As you can see, the format for executable statements is very English-like, and typically they end with a period, not a semicolon as in ALGOL and its derived languages. COBOL has subprograms, but they are not so commonly used. What is more common is to write paragraphs that are called using perform statements, which is the main structuring mechanism for executable statements in COBOL. This dearth of control mechanisms is one of COBOL's weaknesses. That and the fact that it is very, extremely verbose, with every data item being completely specified, and in general there is a lot of writing to be done, as you see here, where we are copying over one record into another. John McCarthy developed Lisp at MIT in the late 1950s for use in artificial intelligence. Its main use is in the processing of data stored in lists. The language is a functional language, with everything essentially written as a function definition. Lists in Lisp are written in a format that is essentially the same as the programs themselves, enclosed in parentheses and separated by white space. There are, for all practical purposes, only 2 data types in Lisp: atoms, which are primitive data items, and lists. Lists are dynamically allocated, and the manner in which they are represented require that their garbage, memory that was no longer in use but not yet available for reuse, be collected and recycled. It also required the extensive use of recursion, and a lot of pioneering work in both problems were done in the implementation of Lisp interpreters. The very fact the language is not imperative is a factor in its relatively slow execution speed on standard computers, all of which are at their core imperative in design. However, there have been computers designed on which they can run more efficiently. Many major AI programs, including Mycin, one of the earliest expert systems, have been written in Lisp. The list is the main data type in Lisp, which makes it stand out from so many other languages. They are typically implemented using linked lists. In the diagram on this slide, you will see that the list A, B, C, D contains 4 nodes, with each of them pointing to the place in memory where the data item on the list is stored. In addition, there is another pointer in each node, pointing to the next item on the list, except for the last one, whose pointer is null. The second list on the slide has the main list contain 2 items that are lists themselves, and the second one has a list within that. For this reason, the nodes point not to a data item, but to another linked list, implementing the list that is the next member of this list. In this way, a list can have members that are lists themselves, and so on, and there can be many lists embedded in other lists. APL is an anomalous language. Ken Iverson designed the language and wrote a book describing the language and wrote an interpreter for it. The main data type of the language is the matrix, and vectors are simply treated as matrices with the width of 1. APL has an extremely rich set of operators, most of them mathematical and many of them involving matrices. The operator set requires a special character set with a special keyboard, or at least a template for it, and for this reason is extremely difficult to read. Here you see a typical APL keyboard. It becomes pretty easy to understand why it is so hard to read. The program that you see here finds all the prime numbers from 1 to R. The last terms are always evaluated right to left unless the order changes due to parentheses. Creates an array of numbers from 1 to R. The down arrow drops the first value, which is 1. The left arrow sets R equal to this array of values. Then a matrix is created that represents a cross product with every multiple of 2 through 6. Then the vector is created with a 0 for the numbers missing in the matrix and 1 for the numbers that are in the matrix. The missing values are our prime numbers. It's easy to see why even Fortran, with its own readability issues, is considered more preferable for numeric work. In the 1960s, there was a huge amount of interest in developing new programming languages. Many of them, like Snowball, were special purpose languages, but there was also a large effort to find a universal programming language that could be used for any programming task, and this led to, among other languages, PL1. PL1 was intended to combine the abilities of Fortran and COBOL, being a language that could be used for either scientific or business computing. It had a syntax very heavily influenced by ALGOL, which made it much more readable than either language. PL1 was a very complex language that could take a semester to learn and a lifetime to master. Despite my own experience in it, taking a semester to learn the language and another 2 semesters in which I used it, it remains a language in which I am not comfortable to program without the manual at hand, and I would not say that about any other language in which I have that much experience. Comments in PL1 begin with a slash and an asterisk, and end in an asterisk and slash, just as in C. The main program begins with procedure options main, and other than the appearance of the options main, looks like any subsidiary procedure. Procedures can appear anywhere within the program, and you could write a procedure right in the middle of the code of another procedure, although this can create major readability problems. There aren't integers, there are fixed numbers, which can actually have a specific number of decimal places. Integers are fixed numbers with 0 decimal places. Many keywords, note that they are not reserved, can be abbreviated, such as DCL for declare, or PROC for procedures. The overall syntax is much easier to follow than that of earlier languages. You will notice that in the previous slide we used getList, and here we use put_skip_list. GetList does unformatted reading, and put_skip_list does unformatted writing on a new line. Read and write are also used, but only for binary files. As you should expect for so complex a language, its compiler is huge and is pretty slow, and the same can be said for the object code that it generates. And the complexity made it difficult to learn, and this made it difficult to find programmers who were competent in it. There was some success with it, and there were companies that used it. But the PC era and the enormous difficulty in creating a compiler for the early PCs helped finish it off. PL1 had some features that found their way into other languages, such as pointers and exception handling. Snowball was a programming language developed for string processing. It was developed by David Farber, Ralph Griswold, and Ivan Polonsky. It was one of several languages developed for that particular purpose. But what made it stand out was the fact that it included string patterns as a standard data type. Its development culminated in Snowball 4, which was a powerful tool in text processing. In the late 1960s and 1970s, other languages were developed for this purpose, including Awk and Perl, which became far more popular. Simula was developed in Norway by Ole Johan Dahl and Kristen Nygaard. For all practical purposes, it was a superset of Algol, and it was developed specifically for doing computer simulations, something that had become a popular application in the scientific community. It is considered the first object-oriented language and introduced the concept of the object and the class. Dartmouth College was the first college to require a computer literacy course, and in the 1960s, computer literacy meant learning how to program. In the 1960s, programming courses usually involved Fortran, or maybe PL1 or COBOL, and it meant working with punch cards on batch processing systems, none of which was user-friendly, and certainly not for English and history majors. That required a language that was somewhat easier to learn, which meant a fairly simple language, and it meant a computing environment that was easier to use, and that meant working on an interactive system, something that was not so common in the 1960s. Kemeny and Kurtz designed the BASIC language, its interpreter, and the Dartmouth time-sharing system, the interactive system on which it ran. These were implemented by a team of students working under Kemeny and Kurtz's supervision. The language included many features from Fortran 2, and it was also influenced by Algol, which was the inspiration for many of its interactive features. The language was easier to learn than Fortran, and programs written in BASIC were definitely easier to get up and running. The language was ported to the Digital Equipment Corporation's PDP computers, running the Ristus operating system, which was actually written in BASIC. This was the version of BASIC and the programming environment that so many college students used in the 1970s to learn programming. This was my second programming language after Fortran. The first program that I wrote in BASIC Plus, as DEC's implementation was called, was a version of tic-tac-toe that the player played versus the computer. BASIC programs back then were line-oriented, and the line numbers were sequential. If the line number for a statement was before the previous line's number, it meant that this line was intended to appear before the lines with larger line numbers. Repeating a line number meant that you were replacing the line. The input statement printed a prompt to the user and allowed him or her to enter a value. In the original Dartmouth BASIC, variables could be only a letter or a letter followed by a digit. The $sign that you see in line 10 means that the variable holds a character string. The absence indicates that the value is numeric. The semicolon after the word in line 20 means that the value appears immediately after the string. If a comma appeared, it meant that the value appeared tabbed over after the string. BASIC had for loops instead of do loops that ran until the next corresponding next statement. Since the for loop in line 50 uses I as a counter, the statement next I ends the loop. Len and left are examples of string processing procedures, returning the length of the string and the leftmost n characters of the string. In the 1970s, there was an effort to make languages simpler and to ensure that syntax and semantics were tied together better. The 1970s led to two languages that became extremely popular, Pascal and C. Despite their popularity, neither language added to the many new concepts of programming language design. There was an effort to add mechanisms to implement data abstraction, concurrency, and verification. CLUE introduced the idea of the cluster, which is similar to the object and the constructor, a method called to help create an object. The issues of concurrent programming first got addressed in the 1970s, and efforts were made to deal with, among other things, the synchronization issues involved. MESA was developed at Xerox PARC to support modular programming and a few operating systems related concerns, exception handling and synchronization. This allowed its use to write programs that could run concurrently and cooperatively. Euclid was also developed at Xerox PARC and was intended for writing verifiable programs. Wirth and Hoare developed the Algol W compiler and later developed Pascal. Pascal's structure and smaller size made it a great language for teaching introductory programming. It was also used to illustrate algorithms. At the same time, it lacked many features that programmers would normally want in a programming language. There was no string type, although you could set up arrays of characters. Separate compilation was not possible, and its input-output facility was not that powerful. Over the years, there were extensions of the Pascal language created that addressed these concerns. UCSD Pascal was developed at the University of California, San Diego. They added features such as the packed array of characters that allowed the program to store more than one character in a full word and manipulate them as a unit. When Philippe Kahn created Turbo Pascal, packed arrays became strings. He also added units to a later version of the compiler and a more practical way of handling input and output, including text and binary files. Pascal fell out of favor in the 1990s as students started learning C, C++, and Java. Dennis Ritchie developed C to simplify the job of writing a new version of Unix for the PDP-11 mini computer. It was based on BCPL and B, where the only data type was the word. C offers 4 data types: the character, the integer, the float, and the double. It also offered 3 modified versions of the integer, unsigned, short, and long, and their size was all linked to the data lengths offered by the computer on which it ran. The basic statement in C is the expression, terminated with a semicolon. This made the assignment operator just another operator from the compiler's perspective, which gave greater freedom when writing programs, as did its loose data typing, which allows programmers to use data items in ways for which the data type was not designed. You could multiply characters, use integers to hold the ASCII values of characters, and even do arithmetic with pointers. All of these encouraged the programmer to write code that did not meet modern-day standards for reliability. C was considered a middle-level language, given its loose data typing. I have often referred to it as assembly language with nicer syntax. C++ does better type checking in many regards, and creates code that is a bit more reliable than C, although it is questionable by how much. As we mentioned before, various attempts were made to introduce data abstraction, concurrency, and verification to programming languages. This led to CLUE, which introduced the idea of the cluster, which is similar to the object and also the constructor. Mesa was developed at Xerox PARC to support modular programming and exception handling and synchronization issues. Euclid was also developed at Xerox PARC and was intended for writing verifiable programs. New concerns came with the 1980s. There was a great deal of interest in adding a mechanism to support abstract data types in programming languages, a mathematical model for certain types of data structures, such as stacks and queues. Both Ada and Modula 2 facilitated this. Object-oriented languages became popular in the 1980s, including Smalltalk and C++. Lastly, there was renewed interest in functional languages such as Scheme, ML, and FP, as well as declarative languages such as Prolog. Ada was designed in 1980 and standardized in 1983. Its main architect was Jean Ishbia, making Ada one of the relatively small number of popular languages that was developed by someone from outside the English-speaking world. Ada was originally developed to help the U.S. Defense Department modernize their approach to developing embedded systems, computer systems that are part of larger systems, such as an elevator control panel or a system guiding a missile or an airplane. Eventually, Ada was required for use in virtually all work done for the Defense Department, replacing not just the massive number of languages used for embedded systems, but Fortran and COBOL as well. Ada introduced the concept of the package, a self-contained software module that provided a good mechanism for implementing abstract data types, and the task, a mechanism for concurrent programming. Although Ada's syntax looks a great deal like that of Pascal, one of its inspirations, all these features helped make Ada a very complex language, and no Ada compiler could be certified without supporting the entire language. This earned Ada the nickname the PL1 of the 80s, and over the years its popularity has waned. The U.S. Defense Department no longer mandates it for use in software written as part of Defense Department contracts. Ada uses 2 dashes to indicate the beginning of a comment, which runs until the end of the line. Using a package requires listing it in a with statement. The use statement makes its contents visible to the program module in which the use statement appears. The procedure AdaX begins with its header and then follows with a type declaration for an array of integers and then some other variables. The block of code starts with the reserved word begins, just as in Pascal, and is then followed by 2 assignment statements, setting values for result and sum. Ada uses get and put for input and output respectively, and begins a loop with the use of the reserved word loop. End loop indicates the end of the innermost loop that is still in progress. The if-then-else construct requires the use of if to indicate the beginning of the construct, then to indicate the statements being performed when the condition is true, else to begin the statements that will execute when the condition is false, and it must be ended with end if. Ada is in some regards very readable. One friend of mine calls it pseudocode with semicolons. But source code written in Ada can get very complex depending on exactly what the program is doing, and this hurts its overall popularity. Niklas Wirth's goal in developing Modula 2 was far more modest. He sought to create a strongly typed language like Pascal with a Pascal-like syntax. It introduced modules which were similar to Ada's packages, and a coroutine, which allowed some concurrent programming. Modula 2 never really caught on, largely because the many extensions added to Turbo Pascal took away much of its potential clientele, and then C became very popular. While it had a lot of potential, it never had the opportunity to live up to it. Smalltalk was one of the first object-oriented languages, and is considered one of the purest examples of an object-oriented language. Its syntax is very different from earlier programming languages, most of which were imperative. Generally, programming problems solved in Smalltalk take significantly fewer programmer hours to solve than the same problem solved using imperative languages. But Smalltalk's syntax was very unusual, and Smalltalk programs ran much slower than programs written in imperative languages. This led to it having limited success. But there was one way in which it was very successful. The experience programming in Smalltalk inspired a Danish doctoral student to develop a language that implemented classes similar to those in Smalltalk, but with a syntax and an efficiency much closer to C. He originally called it C with classes, but it was later renamed C++. The Danish doctoral student was Bjarne Stroustrup. This program defines a class called Polygon. It is derived from the class Object, and there are local variables that belong to each object in the class. These instance variables, in each instance of a polygon that is, are our pen, num sides, and side length. There are several objects or procedures that we can define. New returns an instance of the object. GetPen allows us to get an instance of a pen for drawing a polygon. As you look at the method definition, it becomes clear that the syntax is very different, and this is one of the challenges that Smalltalk provides for programmers unfamiliar with it. and this is one of several reasons why it did not catch on. As I said before, C++ was developed by Bjarne Stroustrup as he sought a language that combined the objects and classes of Smalltalk with the syntax and efficiency of C. While the language was created in 1980, it was not standardized until 1998, and its compilers have not conformed entirely to the standard. Despite this, it has remained fairly popular, with many Microsoft products developed in C++, and with C++ compilers for Windows, Mac OS, Unix, Linux, and many other processors and operating systems. Scheme was actually developed in the late 1970s, but its popularity largely came from the textbook that Abelson and Sussman wrote, entitled Structure and Implementation of Computer Programs. The text was used until very recently in MIT's introductory programming course, and is considered a classic text. There remains a number of colleges who use Scheme in their introductory programming course. ML is a functional language with a syntax similar to Pascal. The name is an acronym for Meta Language. John Backus, the lead developer of Fortran, also developed the functional language FP, which was heavily influenced by APL. Backus believes that it is important that we be able to write programs that can be proven mathematically to be correct. Kohlmarauer, Roussel, and Kowalski developed the declarative language Prolog, short for programming logic, based on predicate calculus and mathematical logic. While the language was actually developed for use in natural language processing, it became very popular in the 1980s for use in developing expert systems, programs that seek to emulate human expertise. The 1990s were dominated by a few factors, and possibly the most significant of these factors was the growth of the Internet. When Bill Clinton became president, he pushed for the National Information Superhighway Infrastructure Act, which led to the commercial growth of the Internet. One of the software projects that grew out of this was the World Wide Web. The World Wide Web was a service developed by Tim Berners-Lee, a British physicist at the European Consortium Lab, CERN, who wanted to share data with colleagues elsewhere, and using hypertext links, a concept that was already around for about 20 years, was key to this. Programming the web led to two problems. If you wanted software passed through the web to be universal, you needed to be willing to share source code and have it interpreted locally. But not everyone wanted to share their source code. You could just pass executable code, but that required knowing the platform on which you were working, and not everyone had the same processor and operating system. That's where Java came to the rescue. Java is an object-oriented language that is sort of like C++, but with the unnecessary stuff taken out, to quote Java guru Elliot Harold. But most importantly, it was translated into an intermediate language called bytecode, which was essentially the machine language for a machine that only existed as a software emulation. This emulation, the Java Virtual Machine, became part of web browsers. Java gave way to several scripting languages, and there were other scripting languages developed in the 1990s, including JavaScript. But the other legacy of Java was its collection of libraries that allowed Java programmers to do an enormous variety of sophisticated tasks. Haskell, a purely functional language like ML, matured, leading to the Haskell 98 standard. Ada matured, leading to the Ada 1995 standard. James Gosling, Mike Sheridan, and Patrick Naughton developed Java originally to provide an alternative to C++, whose libraries greatly frustrated Naughton. One of its first planned applications was for interactive television, but the cable TV industry wasn't interested at the time. It was specifically designed to be simple, object-oriented, robust, secure, platform-neutral, among other goals. They removed many features appearing in C and C++ that they felt got in the way of these goals. The largest part of Java's appeal is not just its portability and use as a web-based language, but also its large library that provides relatively easy windowing capability, networking, concurrency programming, as well as database capabilities. Unlike other popular programming languages, Java remains proprietary, with its intellectual property rights now belonging to Oracle, which bought out Sun Microsystems in 2010. C++ inherited many things from C, including its loose typing, which makes it more difficult to create secure applications than it is in a language that has strong typing, where data items are not allowed to be used in ways that are contrary to their type. Java is considered a type-safe language, meaning that such uses are forbidden. Java supports concurrency, allowing the programmer to coordinate the execution of more than one thread at a time. Java's libraries allow programmers to use it to create applets running within your browser, graphical user interfaces, database applications, and more. The Java Virtual Machine is a software emulation of a computer that doesn't really exist in hardware, and it runs within your browser, allowing Java programs to run on a wide variety of processors running many different operating systems. This has also made it popular for web programming, although there are many other languages that are now also used for that purpose. Java has grown in popularity more quickly than just about any other language,